Okay, perfect. Okay, so welcome everybody to another MCRN Colloquium. Switching over to using a different system, so hopefully it goes well this time. But in testing out our new Google Meet, I have the pleasure of introducing Dr. Yawen Guan. She's an assistant professor at Colorado State University. Before that, she was at University of Nebraska in Lincoln, right? And then before that is when I first met her in 2017 at the Statistics and Applied Mathematical Sciences Institute when it was still around as a postdoc. And so very much looking forward to hearing her talk today on emulation and calibration of an Arctic sea ice model with spatial outputs. So with that, please take it away.
Thanks, Christian, and thanks everyone for attending to my talk. So I'm gonna introduce my work with some of my collaborators here. So this work is a part of a larger project aiming at improving coupled climate simulation in E3SM by improving the sea ice mechanics. So this is a very large group, as you see. We have collaborators from University of New Mexico, Los Alamos, Sandia, and RPI. And I'm one of the statisticians in the group in trying to do some emulation and calibration of the sea ice model. Okay, so why do we model sea ice? I think this group is an expert, but I put this slide in for completion. So sea ice plays a critical role in regulating Earth climate by reflecting solar radiations and insulating the ocean from the atmosphere. Improving the sea ice modeling is crucial for predicting the global climate and support decision-making such as Arctic navigations and understanding the polar ecosystems. So a sea ice model consists of a system of physical equations that describes the various processes governing the state of the sea ice, such as ice thickness, concentration, and motion. And in this talk, I'll mostly focusing on modeling the sea ice motion. Okay, so in this group, we try to enhance the sea ice mechanics, which is has the mechanics to simulate the sea ice breaks and deforms, and the mechanics is allow more accurate simulation of the formation of the ice leads in the sea ice. So the ice model is still through the it's been implemented by into the E3SM sea ice module, and so the final simulation is not available. But I've been running some model runs on the current MPAS-Seaice model, the module within the E3SM model, to develop the statistical method for calibration. So the simulation here I show is for ice concentration. And once I click play here, it's going to show the monthly ice concentrations for roughly a 20-year model run. So for a couple of years of model runs here. So to obtain this model runs, I run the MPAS-Seaice components on the HPC systems. And the model run here I obtain is called standalone configurations, which means it takes the provided forcing data and it only runs the ice module and it doesn't interact with other components in the E3SM model. And the model runs takes about roughly an hour to get 1 year of simulation. And to obtain the model run, I use 15 years of spin up to mitigate the initial effects. So what I'm showing is just the ice concentration, and I can also play a similar animations for the ice velocity for the same region. So here I'm plotting the arrows representing the velocity of the ice. So the color is showing the orientation of the flow, and the size of the arrow, the length, is showing the speed of the ice. So once I hit play, you can see it's showing how the ice is moving over this course of simulation. So in the sea ice model, there are many parameters. Those parameters have physical meanings, and they are what we're interested in estimating. And specifically, I've picked out 6 parameters which have high sensitivities in the model outputs. And these 6 parameters are chosen based on a previous publication on the MPAS-Seaice. For example, one of the parameters control the snow conductivity, and one parameter control the ocean ice drag. The outputs from the Seaice model are multivariate, meaning there's multiple variables being simulated from the ice model. The output is on a 60-kilometer grid, which in terms of the number of grid cells for the Arctic region, it's about 4,700 grid points. Okay, so for the computer model, I can run it at different values of those parameters that I choose. So on the left-hand side, I'm showing a model output corresponding to a smaller drag coefficient. And on the right-hand side, I'm showing the model output corresponding to a larger drag coefficient. And if you compare the outputs left and right, you see that the smaller drag coefficient gives me motion ice velocity that has a larger speed. So the arrows around this area is longer compared to the one with the larger drag. So now comparing this different model outputs, and we want to know which parameter settings I should use in order to generate computer model outputs that's more aligned with what I observed about the Seaice. Then we would like to use observations to constrain the model parameters or to estimate those parameters and quantify the uncertainties in those parameters. Once we're able to estimate these parameters, we can plug those estimates back into computer models and simulate future states of the Seaice. So now on the left-hand side, I'm showing the observations of the Seaice velocity. And if we take the observation and compare with the model outputs that I have and try to see whether a large coefficient or a smaller drag coefficient gives me output that's more similar to observation, you might set a larger coefficient seems to give me outputs that's more aligned with what I observed, since the arrows are about the same size when I compare the two. But now the question is, well, can I adjust this coefficient to maybe something slightly larger or something slightly smaller value in order to get more optimal alignment between the outputs and the observations? And the idea of comparing the observation and the model outputs at different coefficients will allow us to use observation to inform the parameter settings for the computer model. Okay, so my objectives here is to develop a computational efficient methods that allow me to estimate the parameters of the Seaice model using observations. However, some of the challenges here is the ice models produce outputs that's high dimensioned, meaning it has lots of observations in space and over time. So we have a large scale of data that we are working with. And the model outputs are multivariate. We are modeling this concentration, the thickness, and motion, and those are multiple features or variables that we can observe on these for the Seaice. The next is, I mentioned that running the computer model takes quite a lot of time. It takes about a day to obtain a 24 years of model outputs. And so if I want to run this model out, the Seaice model multiple times, it takes a fair amount of time to obtain an ensemble run. And so what we would do is we want to build a statistical emulator that will approximate the outputs from the Seaice model. And we want this emulator to be accurate and computationally efficient. Another challenge is no matter how well we adjust the model parameter settings, it might still be difficult to come up with model outputs that completely agree with the observations due to the imperfections in the model. And so we want to be able to model and capture the discrepancies in the model through a flexible model. So the approach I'm using here, it combines these three main ideas. One is I will use principal components for reducing the dimension of the spatial outputs. And the emulator I will use is called the Gaussian process emulator. We prefer the Gaussian process emulator because it provides not just the prediction, but also uncertainties of the predictions. To model the dependence in the different outputs, I'm using a model called the linear model of co-regionalization. It's a common model used in statistics to model dependence in the different variables. Okay, so now I get into some of the model details and introduce some of the notations for our approach. I will use Z to denote the observations that we use for comparing with the model output. So the observation here are spatial. So I'm putting all of the spatial observations into a vector and use that vector to represent my observation in space. And I'll use theta to denote the input from the for the Seaice model. So those are the physical parameters that I want to estimate. And then I'll let y to denote the deterministic output from the Seaice model under the parameter setting theta. So for every parameter settings I provide to the Seaice model, I can obtain a deterministic output from the model. And here, same thing, the model output I obtained is on space. So I put all the location together and make it a vector of the outputs. So in my introducing of the methods here, I will focusing on the emulation calibration using just the spatial outputs. We are working on an extension to incorporate the multiple time points of the observation and computer model that we can obtain. But for my seminar today, I will only focus on the spatial outputs. Okay, so our goal here is to find parameter settings theta by matching model outputs to observation, such that I want to find the setting that will minimize the differences between the two. Okay, and this is called the calibration. And very often this is done by combining expert knowledge of knowing a certain range for my parameter set, for those parameters, and by fine-tuning each parameter. So if I know theta is most likely to be 0.5, and then I will adjust those values by trying other values like 0.4 and 0.6 and see how the computer model look compared to the observation. However, you can imagine this process is difficult when the model takes a long time to run and when the output of the model is high dimensional. Okay, so in statistics, there is a commonly used framework for calibration published by a paper in Kennedy O'Hagan in 2001. So in this calibration framework, we can set up a hierarchical model for a data model describing the relationship between the observation, the model outputs, the computer model, and delta is called discrepancy term, trying to capture the differences between the best tuned model to the observations. So it's trying to capture some imperfections in the computer model simulation. And then plus an epsilon. The epsilon here, we are assuming that is trying to capture observation errors in the observations. Okay, so the discrepancy term here, because I'm working with spatial outputs. So the discrepancy here is, you can think of it as a function in space, trying to account for the imperfectness in simulating the model output at different region of the Seaice. And we can model it as a Gaussian process. I will explain what a Gaussian process in a little bit more, but it's a flexible model to model a spatial surface. And in this framework, for all of the unknown parameters, we'll give it a priors. So a distribution describing our prior knowledge about these parameters. And then the whole hierarchical model can be put into what we call Bayesian inference algorithms, and to estimate and sample those distribution of the parameters. So I can put this hierarchical model into a flow chart describing the calibration process. And you can think of it as, I will sample iteratively different model parameters theta, and I will generate the model outputs. I will compare it with the satellite data, and if the likelihood function saying it's telling me, oh, the model outputs and the satellite data is close, then I will keep that parameter. And if they're not close, then I will discard the parameters. So that framework is being used to estimate all the parameters. Okay, so for the Bayesian calibration framework that I mentioned, we can sample those parameters by writing out what we call a posterior distribution. And the posterior distribution is proportional to the likelihood function. So the likelihood weighting telling me for this parameter, for the parameter that I sample, how likely is that model output compared to my observation, and plus some prior distribution describing the prior knowledge of those parameters. However, the challenge here is it's very expensive to draw samples from the posterior distribution, because imagine for every parameter, say the physical parameter I sampled, I have to run the Seaice model to obtain some model outputs and compare that model output with observation. And in the algorithm here to make inference, we typically need a large samples. So it's not unusual to draw like 100,000 of samples in trying to approximate the posterior distribution. And if we were to run the model 100,000 times, it's going to take a really long time to complete the calibration. So what we borrow in the statistical literature is called building a surrogate models. There's a really good reference by Bobby Gramercy, published 2020. So the idea here is, instead of running the computer model multiple times, we will build a surrogate model using a statistical approach. So once we're able to approximate the computer model, we will use the surrogate model in our calibration step, which will speed up the calibration process by a lot. And to build the surrogate models, we want a model that will give us, that will be accurately representing the model outputs. And at the meantime, it gives us a prediction of the model output and plus uncertainty of the model output that we're trying to approximate. So I can view the entire process with the calibration and emulation into a workflow that looks like the one in the right. So giving the necessary inputs, the forcings, and the parameter settings to the computer model. Now we will run this many times for different parameter settings to obtain an ensemble of model runs. So here I say we will use n design points, theta 1 through theta n. And for each of those parameter settings, I will run the Seaice model and obtain the corresponding model outputs, y theta 1 through y theta n. Now, given the inputs to the Seaice model and the output of the Seaice model, now we will use this relationship to build a surrogate model. So this is a statistical model trying to learn the relationship between the input and output that would otherwise be described by the Seaice model. So the emulator I will fit here, I use the notation eta, and the eta now will give me prediction of the model output for any input parameter settings that I have not run the model. Now with the emulator, then I will replace it. I will replace the Seaice model in the calibration step with the surrogates, and then combine with model discrepancy and observation error, and compare that with the observation that we obtained from the satellite data. Okay, so to show you what it looks like in a simple case, here I'll use f of theta to denote a scalar computer model output. So this is a simple case where my model would give me only one output. So you can think of this as maybe the Seaice model at one location and one variable. I can evaluate this simple computer model at m design points. So m different combinations of those 6 input parameter that I've chosen for the Seaice model. And then I can record the corresponding outputs as f of theta. So the modeling idea here is we will view this m model output as a realization of a Gaussian process. So Gaussian process is defined by 2 functions. One is the mean function, and one is the covariance function. So the mean function can be any linear function of the parameters, but in my emulator, eventually I will choose a mean function that's equal to 0, which I will explain a little bit more. And I'll focus on describing these covariance functions and what it means here. So specifically, we choose a square exponential covariance function. So this is saying that I will model the outputs f such that the covariance between the f at different settings of theta, they follows this dependent structure where when the 2 parameter settings are close to each other, then the covariance between the outputs will be large, meaning, well, if the parameter settings are similar, then the outputs will also be similar. If the parameter settings are far apart, then the dependence in the outputs will also be small. So one nice thing of using the Gaussian process is that when we look at a finite number of outputs, they follow a multivariate normal distribution. We like this distribution because it gives you a closed form of the likelihood function. And we can also easily write down the conditional distribution of that normal. So with the mean function, I can write down the mean. And with the covariance function, like specified earlier, I can write down the covariance matrix. So the covariance matrix will be a m by m matrix with the elements in the matrix describing the covariance between the f, which follows the dependent structure that I described earlier. So when the points, when the thetas are similar, the dependence between the f are going to be high. when the theta are more dissimilar, then the dependence in the output F would be small. Then once we have a estimate those parameters, now we can use the model to make prediction at a new parameter setting theta. So this theta would be a combination of those physical parameters that we have not run the model, but we want to be able to make a prediction of what the model output will look like. So we can write down the joint distribution for something that we haven't obtained versus F vector, the model output, the ensemble that we have obtained, as a multivariate normal distribution with the mean is being estimated and the variance matrix is also being estimated. Now I can write down a conditional distribution, which is what I will use for making a prediction of the model output as a closed form following this conditional normal distribution. So with the closed form conditional distribution, it just means that I can write down the mean of my prediction and the uncertainty for that prediction. So for this emulator, I will estimate some of the parameters in the Gaussian process using the ensemble run that I have obtained. And once we estimate those parameters, I'll be able to use it for predictions. Okay, and to show you what it looks like in a 1D example, here on the x-axis, I've plotted the theta, the parameter settings. So say here is a univariate parameter. So one parameter I'm trying to estimate. And on the y-axis is the univariate model outputs. I have in the black curve is showing the true function that I use to generate those data points. And the observations is the point in blue. So in this case, I say in the example, I have 5 model outputs. So I know the 5 pairs of theta and F theta. And then using those 5 points, I fit a Gaussian process and use that for prediction for anywhere else in the support of theta. So what you see here, the shaded area is showing the prediction uncertainty, and then the red is showing the mean of my prediction. So what you can see is the Gaussian process is just interpolating between my observations by imposing some smoothness in the curve, as well as providing the uncertainty of that prediction. Okay, so up to here, with the Gaussian process emulator I just presented, it works for a very simple case where the output is univariate. So I want to extend the emulator for emulating spatial outputs. So you could say that, well, I have outputs at each grid point that's univariate, and I can emulate those grid points one by one for each location separately. But this is going to ignore the spatial structures in the model output if we build the emulator independently. And so instead of doing that, we will use principal component ideas by using orthogonal basis calculated from the principal component to try to explain the patterns in my spatial outputs. That way I can have a reduced representation for my spatial output as a combination of those basis functions and their weights. So now for each of the model run that I can obtain, I will project them onto the basis function, and I can record the weights corresponding to those bases. And now for each parameter settings, I'm going to receive a new set of the weights. And the idea is I can just emulate those weights. And once I emulate those weights, which are univariate, and then I can use that emulator to make a prediction at new parameter settings. Okay, so the nice thing of using the basis function representation is that instead of modeling the spatial outputs at each location, now I can project them into a lower dimension and emulate just a few number of those weights instead. And I'll be able to recover the model outputs at a new parameter settings. Another nice thing of those modeling the coefficient is that with a principal component projection, those weights are independent. And so I can build Gaussian process separately for each of those weights corresponding to the different bases. Okay. So like I've mentioned, the bases here that we choose are the principal components because we can choose just a few of the principal components to explain a large portion of the variability in the spatial model outputs. And I haven't told you much about how I obtain those ensemble of model runs. And in the project I'm working on, I use a latent hypercube design to select 80 model runs for 6 different parameters. And so if I put all of the model run together by binding the columns into a matrix, then I can obtain this n by m matrix, which is collecting all of the location and all of the model runs that I have obtained. And to receive the principal components, we can perform a singular value decomposition on this data matrix and retain the first few columns of U as my basis functions to capture the spatial pattern. So in this case, to capture more than 95% of the variance, I only need about 20 principal components, which means I can reduce the dimension of my problem from modeling n spatial location to modeling just the 20 principal components. So in the in this part of the project, I am modeling the velocity field, which is bivariate because there's the UV component of a velocity field. And so to obtain the principal component, I use the idea called the multivariate EOFs. It's very simple. It simply take the U component of the output and concatenate it with the V component of the output and compute the singular value decomposition on this large matrix. So I've plotted the first principal component for the U component and the first principal component for the V components. And what you see is trying to capture the spatial pattern of the velocity field. And the smaller the principal component, so the first few principal component is trying to capture a more of the smooth behavior in the model output. And if you look at the higher number of the principal components, so the 5th one is plotted here, then it's capturing the more of the finer spatial scale patterns in the spatial outputs. Okay. So when I compute the singular value decomposition, I've centered the model output by subtracting the ensemble mean. And then I project all of the model outputs onto the principal component basis, and I can obtain the weights, W, the coefficients, and I can model those weights as mean zero Gaussian process. So in my first presentation, when I present the Gaussian process, I said there's a mean function that we have to model, but because of the centering of my data matrix, I can just model those coefficients with mean zero and just have one less thing to worry about. Okay, so now for each model output, I will do the projection and obtain the weights. And now for M design points that I have run the ensemble, I can obtain M of those weights. for the jth principal component. And now it's nice because the weights are univariate, and I can use the relation, the input-output pairs between the theta and the W to build the Gaussian process emulator. So my notation here for the emulator is eta. It's trained on the jth component weights by using those theta ensemble, the M ensemble that I obtained. And I can use the emulator to make a prediction for any parameter settings theta that I haven't run the Seaice model. And for the weights that I want to predict, I can make a prediction of the mean, and I can also obtain the uncertainty of that prediction. And once I obtain the weights using the basis representation, I can recover the prediction for the Seaice model output. So here's how it works. For a new parameter settings theta star, I will predict the weights using the Gaussian process. In the prediction, I will take the mean prediction and run it through the basis representation and retain the prediction of the mean for the model output. And I can also get the uncertainty of the prediction of the weights from my Gaussian process and obtain the uncertainty for the prediction of my model output. And the computational here is, the computation is very fast because the Gaussian process gives the prediction very fast, and the basis vector computation here is also very fast. Obtaining the variance is also a very fast computation as well. Okay, so back to the original modeling framework that I've shown. I have the observation, the model output. Once I build the emulator, I will replace the computer model with the emulator that I've trained. And now I want to talk a little bit about the discrepancy term, which I haven't explained too much. So the discrepancy term is being used to capture the imperfections in the Seaice model in simulating the true system. And the difference here is going to be modeled for each location of my in my study region. And the reason for that is I want to know how the discrepancy is looked like in, say, some part of the region might be simulating more ice, and then some region is simulating less ice. And I want to be able to estimate that discrepancy function and visualize it in space to tell me, oh, well, this region, maybe the model is underperforming, or in the other region, the model is performing well. So the discrepancy function here is also being modeled with a Gaussian process. However, here the discrepancy is the same dimension as the number of location. And so modeling it with a Gaussian process with such a high dimension can impose some challenge. And so in the next, I'll describe how I will model the discrepancy more computationally efficient way. Okay, so there are some challenges when I model the discrepancy term and the surrogate model, both using Gaussian process, because the Gaussian process is trying to model a flexible functions in space. And when I have two flexible functions in one equations, then it often causes an identification issues, meaning I can't estimate each component separately. And the second issue is when the number of grid points is large. In the Gaussian process, I need to evaluate the covariance matrix for every pairs of location. And that computation can be expensive because I'm dealing with large matrices. And so there are some previous work on trying to deal with the identification issue. Then they proposed this idea called modular calibration. And the idea is to train the emulator first, and then I will fit the Gaussian process in and then I use the fitted Gaussian process in calibration. So I don't estimate the two pieces at the same time. I will do something like a two-stage approach. I will do one GP for the emulator first, and then I'll just use the estimated one into the calibration to avoid the identification issue. So by breaking up the Bayesian calibration, the emulation and calibration in two stages, it also provides some flexibility in how you want to build the emulator. And there are quite a few of Gaussian process software that's available, and those fit very well. That now you can just choose whichever one that you would like to use. Okay, then to handle the dimension issue with the large number of grid points, I use an idea called, it's another basis function dimension reduction approach that I take. So I will model the discrepancy as another representation using basis function. And here I will use what's called Wendland radial basis function for both of the U and V velocity components. So I can rewrite my discrepancy term for, say, the U component as a combination of those basis function that I use the notation K, and I can model those coefficients alpha. So this representation is done separately for the U and V components. And now I need to model those weights, alpha, U, and V as unknown weights, and I want to estimate them. So what does the Wendland basis function look like? Here I plotted 4 basis functions. So those basis functions are defined on the knots, and the knots are distributed evenly in the study region that I'm looking at. So the blue area are the where the ocean at, and the points here are placed such that they doesn't overlap too much. But when you look at the width of the basis, it does allow some overlaps between the different basis functions nearby. So those are the 4 basis functions. And with the basis function and their coefficients combinations, you can think of it as fitting a spatial surface by adjusting the heights of those weights. So with those, you can think of the weights of those sticks that I have here as the value for alpha. So by adjusting the values of alpha, I am adjusting how high my, say, the blanket is. And by once the weights are fixed, then you can think of, now I'm tossing a blanket on top, and the entire blanket is giving me a spatial surface that's trying to model the discrepancy term. Okay, so the weights that I need to estimate. So some of the weights, as you see, they line up in a grid. And the idea here is for the weights that's nearby, they may be sharing similar values compared to the weights that's far apart. So here the weights, we model it as a spatial random effect. So we want to be able to capture the dependence in the value of the weights. So in modeling spatial random effects, here we use a common model that's called the Gaussian Markov random field model. And it basically models the one of the knots as a autoregressive process of the neighbors. So it's saying that my knots, one location is going to be depending on the values of my closest neighbor, and conditional on my closest neighbor, I am independent to the rest of the knots that's far apart. So the nice thing about the Gaussian Markov random field is it has a closed form likelihood function, and again looks very much like the normal likelihood function. Well, it follows a normal distribution, but with the dependent structure that's been encoded in the precision matrix, which is a sparse matrix and can facilitate fast computations. Okay, so I still need to model the dependence between the UV components. It turns out if I want to model two spatial fields that's with dependence across for every location, I want to impose dependence for the U and V observations. We can use this model called the LMC linear model of co-regionalization. A nice thing about this model is I can write down the closed form dependent structure for any alpha U and V for every location. And the number of parameters I have to estimate is few. So I need to estimate the matrix, the elements in the matrix L, and I need to estimate the parameters in each of those spatial random field. Okay, so I'm not getting into too much details of the spatial model, but it just allows me to model each of those sets of weights as spatially dependent weights, and it also allows me to impose dependence between the U and V components. I can write out the dependent structures easily in because it's all in closed form. Okay, so from the original framework where I have model the observation as a function of the Seaice model and the discrepancy term, now we have several dimension reduction that I've applied to the model. One is I reduced the Seaice model by building an emulator on the coefficients and by using the spatial basis function, so the principal components, to capture the spatial variability in the model outputs. And for the discrepancy term, I've again used a spatial model to capture the dependence in the weights, and as well as the dependence across the U and V components. And again, I use the basis function to reduce the dimension of the discrepancy function. So now putting everything together, I have my UV components of observation that's equals to a combination of the emulator, the discrepancy term, and some error terms to capture the observation error. Okay, so I'm showing some of the results. I skipped the algorithms of how to implement it because it's a very standard MCMC algorithm to sample from the posterior. So the inference and the sampling here is quite a standard calculation. And so I skipped that and showing the results that I have applied on some of the synthetic data that I've conducted. So I want to see how my method is working, and so I generated observations from the Seaice model where I take the known parameter values, I run the Seaice model, I obtain the model output, and then I added some model discrepancy term and some observation error to generate my fate data. So the observation that I generated is showing to the right here, and the discrepancy term that I generated is on the left here. And since I'm modeling UV component, I should really showing you a vector field, but it's a little bit hard to see the patterns in the vector field. So here I'm plotting just one of those UV components over here. And once I run through my model and use the MCMC algorithm to sample from the posterior distribution, I can get a distribution of my unknown parameters. So I believe the first one here is the snow conductivity, and oh, sorry, I have it appeared twice, so now I don't remember which one's which. But here is showing the distributions, the posterior distribution for the parameters, and the vertical bar here in vertical line in gray is the value I used to generate my fake data, and the black line here is the distribution that I used to estimate the parameters. So what you see is the peak of the distribution aligns pretty well with the value I used to simulate the data for 1, 2, 3, 4, 5, for 5 of those parameter values. And for the one of the parameter here, I'm not able to, the peak is not very close to the true. However, if you look at the uncertainty of my parameter estimate, it's not too far from, so the true is covered in a certain interval in the 95 credible interval here. And the blue curve here is the posterior distribution using the emulation of one grid point at a time. And that doesn't seem to be able to recover the true parameters that I used to generate the data. Okay, and I also tried to estimate the model outputs and the discrepancy term. So on the left-hand side is the model output from the Seaice model. So that's the true model output. On the right-hand side here is the prediction from my emulator, so from the statistical model. And what you see is the prediction seems aligned quite well with the model output. And in my recovery of the discrepancy term, that also seems to recover the ones I use in my data generation. So this is still work in progress, so I don't have the final results for calibrating the MPAS-Seaice model with the observations. And so from this, the simulation seems to be working reasonably well, and there still require more testing before I apply this to the true data. Okay, to summarize, we extend the 2001 Bayesian calibration framework for univariate data to spatial bivariate outputs for the MPAS-Seaice model. By using the Gaussian process emulator, we're able to do the calibration without having to run the Seaice model thousands of iterations, and that speeds up the calibration process quite a lot. In my model here, I use the discrepancy term that's also a bivariate model to account for the differences between the model outputs and observation. And from the simulation study, it seems that discrepancy term can be recovered quite well from our approach. And this is an ongoing work where we are trying to extend the emulation calibration framework to spatial temporal outputs, and by incorporating more variables and outputs from the Seaice model, including the concentration, thickness, and extent. And we've also had obtained different resolution of the Seaice model outputs. One is 60 kilometer, the other one is 30 kilometer, and we're trying to incorporate different resolution of those Seaice model to come up with an emulator that can make a prediction at the high resolution and use that for calibrations. Okay, so that's all of my presentation for today, and thank you. I want to see if there's any questions from.
Okay, yeah. Thank you, Yawen. That was a great talk. It was really interesting, cool to see. Seems like a really robust framework, I think. Yeah, so anybody has questions, please feel free. I think I heard the hand raise thing go up.
Yeah, I think that was me.
Good.
Yeah, this was really interesting work. Thank you for sharing. I actually, I don't really have any specific questions other than clarifying what version of MPAS-Seaice you're using. Recently, a lot of improvements went into the version of MPAS-Seaice that we use within the fully coupled E3SM framework. I don't know if all of these bug fixes got ported over to the standalone version. And some of these bug fixes make a very drastic improvement to the simulated Seaice. And so I guess I would just encourage you to chat with maybe Adrian, or feel free to contact me. I'll put my email in the chat here.
Thank you, Aaron. Yeah, I
Yeah.
don't know which version I'm using, but yes, I can double check
Yeah,
with Adrian.
Yeah, for the release of E3SM version 3, which came out earlier this year, we made many updates to MPAS-Seaice, and the old code is riddled with bugs, and we fixed a lot of them. And so our Seaice simulation is now vastly improved. And so I would love to see you do all of this with a much more robust version of MPAS-Seaice.
Yeah,
just a word of
that's
caution.
Good to know.
But yeah, there's my email, or feel free to ask Adrian.
Yeah, thank you.
Yeah.
Yeah, I'm probably running the older version because some of this model run I obtained last year.
Okay, yeah. It would be really cool to see this same work on a less buggy version of MPAS-Seaice.
Yeah, absolutely.
Yeah. Anyway, very cool. Thank you so much.
Thank you, Aaron.
Okay, any other questions from?
Question. What are you using to train? You mentioned earlier that you are training you're the emulator first, right?
Right.
And you're looking at the model discrepancy term. So what are you using to train them?
So I use the ensemble runs to train it. So I have run like 80 model runs. So what I get is the input I use to generate the model output and the output I obtain from the MPAS-Seaice. And then from that input-output relationship is what I use for training the emulator.
So by training, you mean that you're just looking at some relationship. You don't have some algorithm that you're using specifically to kind of calibrate that.
Yeah, so the model I use is the Gaussian process model. So it's just trying to interpolate between those observations, the ensemble runs that I have. So the 1D plot that I was showing, I have theta on one axis, and then I have output on the other axis. I obtain some ensemble runs to roughly know the relationships between theta and the output. And then the emulator is trying to interpolate that function.
Okay. I mean, well,
yeah, for the emulator, we're using a Gaussian process model, but people can use other algorithms like a neural network, which will also work, because the goal is just trying to learn that input-output relationship with a model.
Okay. Have you compared it with like a neural network?
No, I have not, but that would be a interesting direction to look into.
Oh, thank you.
Yeah, you're welcome.
I have just kind of one question. It seems like it's a fairly general framework in terms of doesn't really matter as long as you have inputs and outputs, right? You can play this game with the Gaussian process to estimate whatever parameters you're interested in. Is it so it seems like the structure that seems to matter is just having like a state vector and your design points. Is that fair, or is it okay? Yeah, it seems really interesting, and I only bring it up just because it's always fun to put in sort of agnostic algorithms into JEDI. I would like to see more parameter estimation stuff, and if this is, if it can work at a high resolution and deal with the dimension problem, that's really cool. So anyway,
Yeah, so you're right. Like when you choose like the design points to get ensemble run, here we use what's called latent hypercube design. It's trying to expand the parameter space as much as possible. You don't want to have design points that's very concentrated at one region, because then it doesn't allow you to explore, other parameter settings. And yes, we've extended this to a spatial model outputs, and there's more to work on it, like spatial temporal, and then incorporate more of the model outputs as well.
right. Okay. Yeah. So it's not. I guess it's not like an arbitrary. You could just add, because you're doing the velocity for now.
That's right. Yeah.
Yeah. Okay. Would it be hard if you just increase the dimension by, say, one thing like concentration, or does it take special consideration on what the form of the emulator looks like?
Yeah, there are some challenges because the Gaussian process emulator, it's like a normal multivariate normal model, so it requires the output to have a support on the real line. So like velocity isn't too bad, because it has negative value, positive value, and things like that. But when we look at ice concentrations, then there's like there's a bound between the 0, 1, and there's a like large area without ice, and there's some area that's always that has ice. Then it's a mass in the 0 and mass in the 1. Then that is not can't be adequately captured by the Gaussian process model. So there's some way to deal with that.
Okay, that makes sense. Yeah. Okay, cool. Yeah. Oh, that's exciting. It's always fun to have little problems like that. Well, fun in quotes to have problems like that to deal with, right?
Yeah, different problems.
Yeah. Okay. Well, cool. Any other questions for Yawen before we?
I have one last question.
Yeah.
Okay.
All right. So after you reduce your CS model by using the emulator, right, and you have a dimension reduced model for with the vector field that you get, is it linear?
So I use the basis representation. So I have the principal component that I computed, and each principal component is like a map, like a spatial pattern of the model output. And then if you have multiple principal components, then you can think of my way of modeling the spatial output. It's by linear combination of those different spatial maps. And I get away with modeling each single location by now modeling the weights of those basis functions. So instead of modeling a spatial output, I reduce that problem to representing this space into, representing as basis function times some weights, and then I model the weights instead.
I had a quick question about that, actually.
Yeah.
Hey, how's it going? So you're basically projecting your model onto the basis created by the 80 model runs, the real ones.
That's right.
Do you think you're like that could be overly restrictive? Like, would there be a value to maybe adding in additional basis functions like wavelets or something? So you could, because maybe have some structure that's not present in there.
So like wavelets in space, or?
Yeah.
Okay. Yeah. So
I just guess like some other like augmented basis that is not some combination of the few runs you have.
Yeah. So I don't have that like the augmented basis functions in there because the field basis function seems to be capturing a lot of the variability in the model outputs. But what I do have is this discrepancy term with the local basis function that is trying to capture some of the differences between the model output and observation. But if you are thinking of, I want to capture the local behavior in the model output, like how the model varies in performing those modeling, simulating those very small spatial scale patterns, that I don't have.
Okay, thank you. I was just thinking about it. I'm not sure if that would work. I was just trying to get some intuition behind how it's going on. Thank you.
Yeah, yeah, I don't know on top of my head how that will improve the calibration. But it will be good to look into.
Cool. Okay. All right. Well, thank you again, Yawen. I'll send the little clap.
Oh,
There we go.
thank
Yeah.
you.
Be good.
Thanks, Christian.
Yeah. Thank you.
And
Thank you.
thanks
so much.
everyone for attending.
Yeah, cheers. And I guess see you all next week at the regular time, I think.
Okay.
Good.
Bye
Thanks.
bye.